Welcome to my lesson. Today we look at some revision questions in algebra. So we'll be covering a number of topics using these questions. For instance, we'll be covering how to find the GCD using the Euclid's algorithm, and then use that in finding the remainder in modular arithmetic, and also find the inverse of numbers, inverse in modular arithmetic. Then we shall look at the Chinese remainder theorem, among several other topics in today's revision. So I hope you have your calculator, just because most of our questions shall require the use of calculator from the start to the end. Part of these questions are what I gave in my continuous assessment cut, and yet others are just questions in algebra. So let's look at the first question, and we begin by the Euclid's algorithm. Is a way of finding GCD of numbers. We know of several other ways of finding GCD, but we just want to restrict ourselves on the use of the Euclidean algorithm. So Euclidean algorithm uses subsequent divisions. So you do division as you note the remainder at every point. So we're given two numbers, 3 to 1 and 4, 8. So we just want to do division. We want to ask ourselves, how many times does 3 to 1 go into 4 or 8? And what will be the remainder? So you discover that 3 to 1 goes into 4, 8 once. So I write 1 there. 3 to 1 goes there once. And so the remainder will be, use your calculator, but my calculator says the remainder will be 27. What you notice is that if I multiply 1 times 3 or 8, 1, then add 2.7, I would get 4. Now, the next thing is to ask myself, how many times does this remainder go into 3 to 1? How many times? So, using my calculator, it goes there 14 times. So, just use your calculator. So, 14 times. Then 7 goes into 3 to 1, 14 times. And what will be the remainder? The remainder will be 3. Then I ask myself, how many times does 3 go into 27? So I do that until the remainder is 0. And that is when I stop doing my division. So it will go there 9 times. And of course, the remainder will be 0. So in that case, then it means that this is the GCD. 3 is the GCD. So the GCD, and this question said that I should call that GCD as D. So the GCD of 3 to 1 and 4, 8, therefore, is 3. So then I reverse this equation, beginning from where the GCD is. My GCD is 3. I make the GCD to be the subject of the formula. So now reverse, and make the GCD, and make the GCD the subject of the formula. Now we reverse from down going up. When I do this one, I find that 3 can be written as 3 to 1 minus 14 multiplied by 27. 14 multiplied by 27. Now, there's no problem if I was to write here 1, because I know that 1 times 3 to 1 would just be 3 to 1. Now, I want to replace the remainders. So I've already made 3 the subject, and 3 is 3 to 1 minus this. So what about 27? What is 27? So I come here, this is why I have 27. 27 is 4 or 8 minus this. So instead of 27, that's what I write. So I have 1 into 3 to 1 minus 14 into, instead of 27, I write the equivalent of 27 is 48 minus 1 multiplied by 3 to 1. 1 multiplied by 3 into at this point, you would collect the like terms. But first of all, let's multiply negative 14 inside. So if I do that, I would have negative 14 multiplied by 48. And then negative 14 times that gives me positive 14. So positive 14, 381. And then there's another one here, that is plus 1, 381. We just collect like terms. So what we have therefore is that 3 equals negative 14 multiplied by 48. Then what is this? 15 multiplied by 38. So we've written D as a linear combination of the two numbers that we have given. So it's 15 times 3 to 1, then minus 14. So this is what we have and our GCD. So what was the question? The question was, use the Euclidean algorithm to find the greatest common divisor D of 3 to 1 and 48. Then find integer of x and y such that D will be equal to 3 to 1 x plus 481. So our D is 3. What is our x? What is our x? Our x was multiplied by 3 to 1. So our x is 15. And then our y was to be multiplied by 48. So that is negative 14. So that is what we were supposed to repeat. Now I want to look at the next question again, just another example of how to use the Euclidean algorithm to find the GCD. And then after finding the GCD, write the GCD as a linear combination of the two numbers. Maybe one more example will make this clear. So this is my next example. Say use the Euclidean algorithm to find D, the GCD of these two numbers, and then write D in the form of B. So we just take the largest of the two numbers, that's 672, and we ask ourselves how many times does 15 go into this number. And using my calculator, I find that it goes there twice. So it's 2 times 15, 52. I'm going slowly so that you can get to know what I'm doing here. For those who are not familiar with this method. Now, what is the remainder? It goes there twice, and the remainder using my calculator will be 540. Then I ask myself, how many times does 540 go into this? So I'm now using this remainder to do that. So 15, 66, 540 goes there twice. 540 goes there twice. And the remainder therefore is 46. The remainder is 46. Remember, we have to do that until the remainder is 0. That's the time we stop. And then we read our GCD. Now, so how many times does 486 go into 540? 540. 486 goes there once. And what is the remainder? The remainder is we subtract 54. 54 into 486, it will be it goes there 9 times. 9 times. And the remainder is 0. The remainder is 0. And therefore, 54 becomes our GCD. So our GCD, therefore, our GCD of 36 72, which we can also call D, as per this question, is 54. So again, as we did in the previous question, we reversed from here, going up, and make it for the subject of the formula. Make it for the subject of the formula. So when you reverse, it becomes 540 minus 1 multiplied by 46. As I did earlier, I can put a 1 there because I know that multiplying 1 by 540 makes no difference. Now I substitute the next remainder, which is 486. It's here. I make it the subject and then substitute there. So this is the same as 540 minus 1 multiplied by, instead of 486, I know that 486 will be the same as, I take this the other side of the equal sign. So 486 will be the same as 1566 minus 2 multiplied by 540. You can also put a 1 here if you want. You can put a 1 here in brackets, because I know that 1 times that makes no difference. So this will be the same as 1 multiplied by 540. Then let me multiply this inside this bracket. I would have 1 multiplied by 1566. Then this negative 1 times that will be positive 2, 540. Collect like terms, negative 1, 1566. This is positive 2 and positive 1 there, that gives us positive 3, 540. Now, so we need now to substitute the next remainder, which is 540. So that is negative 1 here, 1566 plus 3. Instead of 540, instead of this 540, we know that is the same as, take this to the other side of the equal sign, it will be 3672 minus 2 multiplied by 1566. Close the bracket. So when this happens, what do we get? I just want to begin with this bracket, expanding the bracket there. There's no problem. I can begin from anywhere. That will be 3, that's 6, that's 672. This 3 times this negative 2 gives us negative 6. Negative 6. 1566. Then remember this one. That was negative 1, 1566. Put the like terms together. What I have there is 3. That's 672 minus this negative 6, negative 1, that would be negative 7. 1566. And we are done because we've substituted all the remainders. So that means 54 can be written as 3 multiplied by 3622 minus 7 multiplied by 1566. So that is how we do, how we find the GCD by the Euclid's algorithm, and that is how then we write that GCD as a linear combination of the two values. So we then look at the next question. Just before the next question, I've given this exercise for you to try to apply the Euclid's algorithm that I've just talked about, that I've shown you two examples. They use Euclid's algorithm to find the GCD of these two numbers and then express them. And I've included my answers. I expect that when you do it, you get that the GCD will be 17 and this will be the answers. And you also try this one. Yes, so just using the same method I've showed you about. and the answers are there. Now, so I want now to use the Euclid's algorithm to try and look at something different, what we call the linear congruences. Want to find the value of x. Now, this is mod 23. If the moduli is smaller than 10, you can use trial. But if the moduli is greater than 10, then I want to show you that we can only use the Euclid algorithm. Although you can use trial, but you see you're trying numbers you're trying mod 23. Mod 23 means these are values 0, 1, 2, 3, all the way up to. So you have to try 0 to 22 and see which one would, when multiplied by 5, gives you a remainder of 12. What is here is the remainder. What is here is the remainder. So when you multiply x by 5, then the result is divided by 23. Which of these values would be multiplied by 5 and divided by 23 to give you a remainder of 12? So you can see that if the module here is larger, then you have so many values to try. And so that will waste a lot of time. So there are various ways of solving this. You can, for instance, find the inverse of 5 and multiply by the inverse of 5 on both sides. And when you multiply 5 by its inverse, this value here leaves with an x. And so what you have here would be the result. But that method I'll show you later. What I want to show you is the Euclid's algorithm that we just learned in the previous two examples and use it to find the value of x. So the question is, find this. Now, a few rules before we proceed. Before we proceed, if you're given ax is congruent to b mod c or mod m, first of all, see whether the GCD find the GCD of a and m. If the GCD of a and m is n, check whether this GCD n divides, whether it divides b. And I'm using this particular line to mean divides. So you check to see whether the GCD divides b. If the GCD does not divide b, then this congruence has no solution. If the GCD of a and m does not divide the value here, then this congruence has no solution. But if the GCD divides this value here, if it divides b, if our GCD n divides b, if n divides b, then the congruence has a solution. Has a solution. Not necessarily one solution. It will have several solutions, but it will have one solution. But what is important is that if n does not divide b, if n does not divide b, just use the vertical line, then cross it to mean does not divide. If it does not divide b, then this congruence has no solution. Has no solution. But if it divides, then the congruence has a solution. Now, if it divides, how many solutions will this congruence have? If it divides, then this congruence would have how many solutions? You will have n solutions. So if the GCD is n, and n divides this value, then this system has n solutions. So I'll take two examples just to illustrate that. Now, I've already given some good rules that will guide us in doing this kind of questions. And with the first thing I say is that we find the GCD of 5, the GCD of 5 and 3. This one is easy because we can see that this GCD is 1. Otherwise, if the GCD is not easy to see, and then it would be easier for us to use the Euclidean algorithm to find that GCD first over. But for this case, I can just see that this is 1. And I can also see that 1 and 1 divides, I can see that 1 divides 12. So it means then the congruence has a solution. How many solutions? The number of solutions must be equal to the GC. So the congruence has one solution. So then we want now to find that solution. So that means then we must use the Euclid's algorithm. So whichever way, you can never avoid this, finding the Euclid's algorithm. So we take 23, and then we ask ourselves, how many times does 5 go in 23? And we find that 5 to go there 4 times. What have I written? I've written 12 instead of 23. It's supposed to be 23. Supposed to be 23 there. So 23. 5 goes in 23 4 times. And what is the remainder of the 3? So 3 into 5, 3 into 5 would be 1s. The remainder of the 2 is doing until the remainder of 0. And the 2 into 3 is the 1s. And the remainder of the 1, 1 into 2 is the twice. The remainder of the 0. So our GCD is, as we had already said, is 1. So we reverse from this GCD going up. So reversing, what do you get when you reverse? 1 is 3. I didn't need to put the bracket there. So it's 3 minus 2. So 1, this one is, I'm just taking this on the other side of the equal sign. Just taking this, the other side of the equal sign to be 3 minus that. And so I want now to replace the next remainder. The next remainder, that would be, what is that? I take this on the other side of the equal sign. So it will be 5 minus 1 multiplied by 3. Open these brackets. I have negative 1 multiplied by 5. I have this to be positive 1. Positive 1 times 3. Then plus this 1 will be 2 multiplied by 3. I've already corrected left term. Because this would be positive 1 and there's another positive 1 here. That will be positive 2 multiplied by 3. I now want to replace the next remainder, which is 3. So this will be negative 1 multiplied by 5 plus 2 into, instead of 3, we have 23 minus 4 multiplied by 5. We make these points. What do I now have? Negative 1. Now let me write this one first. What is this? This was 23. This was 23. So 2 multiplied by 23. And then these 2 times that will be negative 8. Negative 8 times 5. But there is a negative 1 here. So when you factorize that, you have negative 9. Negative 9 multiplied. Yeah, because this was negative 8 times 5, and there's negative 1 times 5, that gives negative 9. So we've obtained that we've already done, we've replaced all the remainders. Our last remainder was 3, and it's what we replaced here. It was 23 minus 4 multiplied by 5. And so what this means, therefore, is that 1, which is our GCD, can be written as 2 multiplied by 23 minus 9 multiplied by 5. That's what it means. So 1 here is the remainder, therefore. 1 here is the remainder, but our question has the remainder as 12. Our question has the remainder as 12. But what we have here is that 1 is the remainder. So what that means, therefore, is that I make this the remainder to 12. So how do I make this remainder to 12? I do that by multiplying the entire equation here by 12. When I multiply the entire equation by 12, I'll then get 12 into congruent. In fact, we can use a congruent. I can use the equals, but it's okay. So long as you understand what we are doing here. So I'm multiplying the entire equation by 12. When I do that, I'll get 12 to congruent. So I multiply what is it? Then you just follow what is in bracket by 12. So multiply that by 12, it is 24. 24 in bracket, 23. Then this one by 12, 108, 108, 5. But let's remember that we are doing it mod 23. So we reduce everything to mod 23. This 24 reduced to mod 23, and this 108 reduced to mod 23. So we're asking ourselves that if 23 were to go into 12, what would be the remainder? Into 24. If 23 were to go into 24, what would be the remainder? So this is the same as the remainder would be 1, followed by 23. And then what about if it was 23 were to go into 108? If it were to go into 108, I'm getting that the remainder would be 7. And the remainder must always be positive. The remainder would be 7. The remainder would be 7. Let me just show you how I get that with my calculator. Let me see if 23 were to go into 108. How many times would that be? Let me just do it here. If 23, let me just do it here so I show you. 23, if 23 were to go into negative 108, it would be 5 times. And so what would be 5 times 23? With my calculator, 23 times 5, not 5, but negative 5 times. Negative 5 times. So that 23 times negative 5, my calculator says that I'll get 115. Negative 115. So when I subtract these two, just see what I get. So I just take negative 108, then minus, just a minute, negative 108, then minus 115, which is the same as plus 115. And when I do that, I get 7 as well. I get 7. So the remainder is supposed to be positive. That's why I say that 12 can be written as 1 multiplied by 23 plus 7 multiplied by 5. In fact, if you try your calculator, you find that this is true. That 1 times 23 plus 7 yes, plus 7 times 5 would be 12, and we are doing it mod 23. We are doing it more. What you're saying, what will be the result? What you're saying is, this will be 23 plus what? Let me just tell you, let me just show you what I'm doing. I want to show that this is the math 12. So what are we doing? It's 23 plus, my calculator is not very visible, but I will do 7 times 5, which is 35. So that would be 58. But then we're asking ourselves, is 58 the same as, is it congruent to 12? We're asking ourselves, mod 23, is 58 congruent to 12? In other words, if 23 were to go into 58, would the remainder be 12? Let's see. We'll go there twice. We'll go there twice, 23 go there twice, so we get 46. So what is 58 minus 46? And the 2 is 12. It's 12. So this is correct. This is correct. So remember, you are doing it mod 23. Now, but that is not very important. What is important is that we use Euclid's algorithm, and we found that the GCD was 1, and so when we came up to here, we discovered that this question was telling us that 1 would be the remainder. If, yeah, here, when you work out this, the remainder would be 1. Mod 23, work out this, the remainder is 1. The one that we have here. But what we want to be the remainder is 12. So then I multiply this equation by 12. And then after multiplying by 12, I reduce it to mod 23. So I arrive at this. What is the question? The question is, what can be multiplied by 5? What can be multiplied by 5 to get it 12? I can see from here. What I can multiply by 5 from here is 7. What I can multiply by 5 from here is 7. So that means x is 7. If you want, you can say mod 24. X is 7. So what I mean, therefore, is that if I have 5 times 7, and then this result divided by 23, the remainder will be 12. First, this will be 35. If I multiply by 23, the remainder will be 12. That's what it means. So I was looking for value which, when multiplied by 5, and then the result divided by 23, the remainder will be 12. And that x is just 10. I want to take one more example to make this here. So I want to look at this example. An example says, what value when multiplied by 22 and divided by 143 will leave a remainder of 8. So first of all, I want to see what the GCD of 22 and 43 will be. And as I said earlier, that if you cannot easily see what the GCD is, then just use the Euclid's algorithm to find the GCD. But from here, I can see that the GCD of 22, 143, of course, I can see easily that it will be there. And I can also say that 11 does not divide 8. Does not divide 8. And for that reason, this congruence has no solution. The congruence has no solution. So you don't need to waste your energy solving this because you'll find no solution. Let's look at another example. Now, let's look at this question. It introduces some slightly new concept where we're getting several solutions for some congruence equation. Now, this we are given 9, so we find the GCD of course, of 9 and 30. And that gives it 3. And it's clear that 3 divides 21. And so, therefore, the congruence that we are given, this congruence has solutions, has 3 solutions. That's what we say. We said that if the GCD divides this remainder, then the number of solutions will be equal to that GCD. In this case, our GCD, which is 3 divided by this remainder, therefore, our congruence has 3 solutions. Let's now work out. Now, when you discover that we have GCD, which is now dividing this remainder, the best thing is first of all, divide the entire equation. Divide the entire equation, the congruence, by that GCD. Divided by GCD. So when you divide the entire thing by GCD, you get the result is congruent to 7 or 10. So I just divide the entire thing by 3. 3 here will be 3x, 3 here will be 7, and 3 here will be 2. Therefore now, this is my new equation. This is my new equation. I just call it equation 2, where I now assume that this is my equation 1. Now, what I want to solve therefore is this equation 2. And of course, you can see that this equation 2 has a solution, because the GCD of 3 and 10 is 1 and 1 divided 7. So therefore, let's use the Euclid algorithm on 3 and 10. Through go there 3 times, and the remainder will be 1. And into 3, 1 will go there 3 times, and the remainder will be 0. So we then reverse the equation. So, of course, the GCD is 1. GCD is 1. So then that's just reverse. Just reverse that equation that I've talked about. And so what is 1? 1 is 10 minus 3 multiplied. So what do we require here? We need a value which, when multiplied by 3, will give us a remainder of 7. But what do we have? We have a value which, when multiplied by 3, gives us a remainder of 1. We want a remainder of 7. We have a remainder of 1. That means this equation 3, we need to multiply by 7, so that we have a remainder of 7. So multiply equation 3 by 7. I think I'm slow so that you can get what I'm doing. Multiply equation 3 by what? By 7. By 7. Multiply equation 3 by 7. Because we want a remainder to there, our remainder to be 7. So when I multiply equation 3 by 7, I will have 7 is congruent to 7 multiplied by 10 minus 21 multiplied by. So what do I have? I have an x which, when multiplied by 3, gives us a remainder of 7. That x is negative 21. And the new module here is 10. So what is this module 10? In other words, how many times does 10 go into 21 negative? What will be the remainder? What will be the remainder? So how many times do you think 10 goes there? 10 will go there negative 3 times. Let's see. Go there negative 3 times. So that gives us negative 5. So when you subtract, you have positive 9. a positive 9. So that means x therefore is 9. But we said that this system would have 3 solutions. So the first solution therefore is 9. How do you get the second solution? You take the first solution plus the module here, plus this module here, this new module, which is 10. That gives you 19. And how do you get the third solution? The third solution, just take 19 plus this module again, plus this module is 10, that gives 1. The fact that I'm saying therefore is that the general solution will be given by x1 plus n multiplied by the new module. Let me call the module m, where n are the numbers 0, 1, 2, etc. In this case, we need 2 solutions. So our n will be 0, 1, and 2. 0, 1, and 2. That means when n is 0, then x becomes 9. Because it will be 9 plus 0, 10. That gives us 9. When n is 1, then we have 9 plus 1 m. M is 10. 9 plus 1, 10. That is 19. What about when n is 2? When n is 2, we have 9 plus 2m, but m is 10. So that is 2 times 10. That gives us 20. That's how it is 9. So these are our 3 solutions: 9, 19, and 29. Those are the required values of x. Those are the required values of x. You can look for another example just to emphasize this idea. This I consider the GCD of 7 and 24 is just 1. So this and 1 divides. Remember that you must check whether the system has a solution before you begin doing it. So 1 divides 3. So the system, so this congruent has a solution. In fact, it has just one solution. One solution. So let's now find out what the Euclid's algorithm would say about this. 7 will go there 3 times because of 21, and 21 subtracted from this you get 3 as a remainder, and 3 will go into 7 twice because of 6 and the remainder of the 1, and of course the 1 will go into 3 times and the remainder will be 0. So we reverse these equations beginning with this. So reversing, let me reverse from here. Reversing, what do we get? So when you reverse, we have 1, which equals to 7 minus 2 multiplied by 3. Yes, I've just taken this on the other side of the equal sign. Then this is the same as 7 minus 2. Now I substitute 3 with what? Next 3 is substitute the formula here. 3 is the same as this minus that. 3 is the same as this minus that. So 3 is the same as 24 minus 3 multiplied by 7. And you can just put a 1 here, and just put a 1 here, there's no problem. Now, so let me begin by opening this bracket, and so what I have is negative 2 multiplied by 24, and then negative 2 multiplied by that, which is negative positive 6 multiplied by 7. And then there's this 1 multiplied by 7. what does it become? Negative 2 multiplied by 24 plus 7 multiplied by 7. That is what gives us the remainder of 1. So this will give us that. So the remainder here is 1. But we require a remainder of 3. We require a remainder of 3. So I think this thing is becoming clearer to you, that I want to multiply this with question 1 by 3. Let me just do it here. When I multiply this equation by 3, I have a remainder of 3 here. And then here I have negative 6 multiplied by 24. And here I'm multiplying it by 7. Is it? What am I multiplying by? Multiply by 3. So this is by 3. This is by 3 negative 6. This is by 3 to 21. Positive 21. Multiplied by 7. Remember that our mod is 24. And the value here should be less than 24. Now, I'm not bothered about this. Of course, if I was bothered, I would want to make it positive. But why should I be bothered with it? Because I only need what I can multiply by 7 to get 3. And I'm still have it. I have it. That x is 21 mod 24. So what I'm saying therefore is that if I multiply 21 times 7 and then divide the result by 24, the remainder will be 3. That's what I'm saying. And that's why I say that I'm never bothered by this. I don't want to go there. But you can still do it if you understand. Make it positive. It's mod 24. Doing mod 24. I'm doing this mod 24. Just not add it 24. And it will be 18. Just add it to 18. If you're bothered by this, then just write this. Just write it as 3 is congruent to 18, 24 plus 21 multiplied by 27. No, multiplied by 7. Multiplied by 7. If you're bothered by it, then let's go. Let me just confirm if that is clear using my calculator. Using my calculator, what is 18 times 24? And then plus 21 times 7. The result that I get divided by 24. The result that I get, I want to divide it by 24. So what am I getting? I'm getting 576. 576. No, 579. 579 divided by 24. 579 divided by 24 goes by 24 times. So 579 minus 24 times 24. The remainder is 3. That's correct. That's correct. The remainder is 3. So that's why I was saying that if you're bothered by this, just add a negative 6 to 24 and get it, the remainder as positive. Or if you want, just say how many times does 24 go into negative 6, and you'll find that it goes by negative 1 times. So negative 1 times 24 will be negative 24 times. When I subtract negative 6 minus negative 24, the answer is 18. You're bothered by this. But for me, I wasn't bothered by it because I knew I wanted what would be multiplied by 7, and I already had it. I already had it here. I already had it. So why go into some other words? I already had that. So let's look at another example. Now this one, by looking at it, I can never tell what the GCD is. So let me just work out the GCD because it's not easy for me to just tell what it is by looking at it. So I'm looking for the GCD of 381 and 48. So 48, 381 of course got there once. Let me just use my calculator to see what the remainder is. And the remainder of course is 27. The remainder is 27. Then 27 into 381. How many times? 14 times? Yes, 14. What's the remainder? The remainder is 3. And then 3 into 27, it's 9 times. The remainder is 0. GCD is 3. Can 3 divide 231? How many times? 7, yeah, 77 times. 77 times. And so the GCD is 3. And 3 divides 231. So the system has 3 solutions. So we need to obtain 3 solutions. Now, what did we say in the previous example? We said then we now divide this GCD through, because it's common to all the 3 terms here. So we divide it through. Let me just create some space. I want to call this equation 1. Now, I just continue with my working. Now divide equation 1 by 3 to get. And so let me just divide that with my calculator. What am I getting? 127x is congruent to, let's say 77 mod 136. Mod 136. So this is what I want now to solve. Of course, it has a solution, one solution, because the GCD of 127, 136 is there for 1, and 1 can divide 77, so it has a solution. Now, so let me now use the extended Euclid's algorithm, Euclidean algorithm. So we ask ourselves, how many times does 127 go into 136? What is the remainder? The remainder is 9. And 9 into 127, how many times? It goes there 14 times. 14 times. The remainder is 1. And 1 into 9, how many times? 1 into 9, 9 times. The remainder is 0. So let's reverse now from reverse. This will be 1. Make 1 the subject because it's the GCD of this new question. Of course, this new question I'm calling it 2. Calling equation 2. So it's the GCD of equation 2. So let's reverse. So this will be 127 minus 14 multiplied by 9. So what is the 9? Replace 9. Using the first equation, 9 is the same as 136 minus 2. So you take this on the other side. That is 136 minus 1 multiplied by 127. And so what does this give you? It gives you negative 14 multiplied by 136. I'm just began by opening these brackets. And that would be positive 14 multiplied by 127, and there is a 1 here. That is positive 14 plus this 1, that gives us positive 15 multiplied by 127. So in fact, the remainder, this was 1, this is 1. just coming with 1. So it means that if I multiply 15 by negative 127 and divide the result by 136, the remainder will be 1. But that is not what I want. What I want to be the remainder is 77. 177 to be the remainder. 477 is the remainder in question 2. So I want to call this equation 3 and multiply this equation 3 by 77. Multiply equation 3 by 77. Just get some space, bracket, some space. But remember the moduli of equation 2. Remember the moduli of equation 2. You have just erased it. Remember it, because we will require it. So what do I get when I multiply 77 by equation 3? I will get 77 is congruent to negative 14 times 77 multiplied by 136 plus 15 multiplied by 77 multiplied by 127. So what I want is what value, if multiplied by 127, will give me a remainder of 77. So that value is this. So that means x is therefore 15 times 77 mod 136. Let me just find out what that is. I just want to multiply 15 by 77, then divided by 136 and see what the remainder is. 15 times 77. I hope you are doing it together so that 15 times 77, I'm getting 1155. 1155 divided by 136. 1155. Let me just write it down. 1155 divided by 46. 8 times 1155 minus 8 times 136. Was it 8 times? The remainder is 67. The remainder is 67. So this the remainder can be reduced to 67. This remainder can be reduced to 67. Because the remainder must always be less than the divisor. The remainder must always be less than the divisor. So when you find that the remainder is bigger than the divisor, you continue reducing it. So my x1 therefore, this question had 3 solutions. We found one, getting space to write the other 3, the other. So we can write the general solution. Therefore, we can write the general solution. So the general solution is x is 67 plus n m, where n is 0, 1, 2, and m is 136, our mode, our new mode. So that's why I say that x1 is the value when n is 0. So when n is 0, the entire this becomes 0. We have 67. About x2, when n is 1, so 1 times m is 136. So it will be 136 plus 67. When I use my calculator, I get it to What about when n is 2? 2 times 136. 2 times 136. Then add to 7. The answer will be 339. So those are the 3 values. Oh, so I can call them x3. Call it x3 as 3. So those are the 3 solutions for this conference. And let me look at this question here. Find, just get my pen first of all. Find the integer q and r such that if 13 were to divide into 54 negative 54, the quotient will be q and the remainder will be r. We just want to find q and r such that negative 54 will be the same as 13 times something q plus r, which is them. So that is very easy. Just took 13 and divide into negative 54 and see what the quotient is. Let me just give my carpet. But I will take 54 negative 54 divided by 13. I can see 4, but now I take negative 5. I take slightly higher because I want the remainder to be positive. Take negative 5. Instead of negative 5, take negative 5, so like that. But now, what is negative 5 times 13? That will be negative 65. Negative 65. Subtract this. So it's the same as negative 54 plus 65, which then my calculator says will be 11. So this is the remainder. So it means negative 54 is the same as negative 13 times negative 5 plus the remainder 11. In other words, q is negative 5 and r is 11. So that is how this question is supposed to be done. So I clear it. And then we'll look for the next. The next is just exercise 2, where I use the concepts above to solve this congruence equation. Of course, we only solve where there are solutions, and where there are no solutions, we say why they are not. For instance, you get that the GCD does not divide the remainder, then in that case, there is no solution. So that becomes the reason. That is the reason as to why there is no solution. Now, so I want to now show you how to find inverse of modular arithmetic. And again, as I said earlier, there are so many ways of finding the inverse in modular arithmetic, but I stick on the Euclidean algorithm because it's now what you're familiar with, because it's what I want to just show you how to use it to solve as many problems as possible in this video. But I know there are other ways of finding the inverse. You have the Fermat's, the little Fermat's theorem, you have the Euler-Phi theorem, and there's so many other ways of finding the inverse of in modular arithmetic. But I want to pick on what I've already showed you. That is Euclidean algorithm. So then you realize that the Euclidean algorithm is a very powerful tool in algebra. It's a very powerful tool. One, the inverse of so this question is the same as find the inverse of 100 or 20. It's a question. Just find the inverse of this model. Or somebody can say find the inverse of 100 in Z over the 20. It's the same question. Find the inverse of 100 mod 27 or find the inverse of 100 in Z 20 mod 27. And we will just use the Euclidean algorithm. Just erase this. So of course what we have here is 120. We ask ourselves how many times does 120 get? How many times does 100 go there? And using a calculator you find that it goes there 20 times. 100 goes there 20 times. And the remainder is 11. And then we ask ourselves, what about 11 into 100? How many times? Calculator says goes there 9 times. Times 11, that would be 99, and the remainder would be 1. And so what about 1 into 11? We put there 11 times. The remainder would be 3. So with that, we then reverse this. Reverse going up. Reverse going up. So 1 is 100 minus 9 multiplied 11. Now substitute 11. We want to write a 1 here. 9 into 11 is the same as, take this on the other side of the equation. Plus 2011 minus 20 multiplied by 100. Collect like terms. So this will be 1 multiplied by 100. 9 multiplied by 2011 plus 9 multiplied, not 9. This is 180. This is 180. 180. It's plus 180 multiplied. So what do we now have? What do we now have? What we have is 1 is negative 9 multiplied by 2011, and this is 181. 181. Just write it properly. 181 multiplied by. Now, so what was the question? Let me just tell you what the question was. The question was, what number, when multiplied by 100, you get 1? That is what we know about the inverse. Because the inverse of A under multiplication is B if the product of A and B gives us 1. The inverse of A is B if this product gives us 1. That's what the question wanted. What value when multiplied by 100 gives you 1? We are seeing here. We are seeing that when 181 is multiplied by 100, the result is 1. So solution is the inverse of 100 mod 2011 is 180 as the inverse. And if you want to write it as 181 mod 20. So that's the inverse. That is the inverse of 100. And you see what we've done. Just use the algorithm and the reverse. And we read the value. I want to show another example. Now, so this question wants us to find the inverse of 56. But somebody can write it this way. Somebody can write it this way. 56x is congruent to 1 mod 9. The same thing. That we are looking for value which, when multiplied by 56, would give you 1. That is the inverse of 56. The inverse of 56 would be a value which 1 multiplied by 56 gives you 1. So this question, somebody can write it this way. Or another person can say, find the inverse of 56 mod 93. The same thing, the same thing. So of course, this kind of question we've done it, seen it before. And this is what we are just doing. It's what we are doing. So that means we find the extended Euclid's algorithm. Just look at my pen. We did extend it as I show you us last time. We have 93. This pen that I have writing and then pick them up. This one is this one is okay. So 93, how many times does it repeat theorem? Since those are ones, what's the remainder? Let me subtract 6 from that, I get it at 7. That's 7 into 56, again it will be ones. What is the remainder? 19. 19 into that 7, again it will be ones. Or the remainder is it 18. 18 into 19, again will be ones. Or the remainder. And then 1 into 18, it will be 18. The remainder of this group. And then we make 1 the subject. The first thing. So the first equation here is 1 is congruent to 19 minus 1 multiplied by 18. You can put a 1 here. So this is the 1 multiplied by 19 minus 1 multiplied by 18. But what is 18? What is this 18? 18, I take this to the other side of this equal sign and find that 18 is that 7 minus 1 multiplied by 19. Multiply this. I can put a 1 here. Open this bracket. I have 1 multiplied by 7. And this is negative times negative. Negative 1 times negative 1, which is positive 1. That positive 1 plus this 1 give me positive. Multiply by 19. So I want to substitute this 19 here. This is the 1 multiplied by 7 plus 2 multiplied by 19. But what is 19? 19 is 6 minus 1 multiplied by 7. So I'm showing you this way of finding the inverse value. You won't use guesswork. You're doing the inverse of in modern arithmetic. You don't use guesswork. Use Euclid's algorithm. And as I said, there are various other ways of doing it. But I've chosen on this. Now, so I can put a 1 here. And so when I do this, I have, I want to open this bracket. I have 2 multiplied by 6. And then this by that, I have negative 2. Negative 2. And this one is positive 1. Just want to verify whether it's okay. Let me just go back to where we began. This is 19 or 18. When you open the bracket, I thought this was negative 37 and this was positive 19. So 1 level was a 2. That's okay. So that will then be 256. I think there's a problem somewhere. There's a problem somewhere. Let me just go back. Yeah, the problem is this negative multiplied inside. This will be negative. This will be negative 137. And this will be positive 19. This is positive 1, positive 1 times 19. Positive. But this is a problem. It's supposed to be negative. This is supposed to be negative. Yes. So that I have 256. You see, how did I discover there was a problem? Because the signs are always supposed to be. If it's negative here, the other one must be negative. If it's positive, the other one must be. We can never have this one being negative and the other like term being positive. No, they must be the same. So this is negative 2 and negative 1, which would be negative 3. That's it. Yeah. So yeah, it's very easy to discover when you're going wrong. If this is negative, this must also be negative. So then you can now substitute that 7. Because that is where we are. Now substitute that 7. So this would be 2 into 6 minus 3 into. Instead of that 7, we have 93 minus 150. Just want to get some space a bit. Get space. Remember that we are looking for value which when multiplied by 6 would give us 1. So let me just pick my pen again. Yes. Let's open that bracket. First of all, I would have negative 3 multiplied by 3. Then negative 3 multiplied by positive 3. That positive 3 plus this to be positive 5 multiplied by 6. I think that was the last replacement required. That was the last replacement. So we wanted a value which, when multiplied by 6, would give us 1. And so that value is 5. So that means the inverse of 56 more than 3 is 5. More than 3. So 5 is the inverse of 56. So in other words, if I took 5 and multiplied by 6, and then divided that result by 3, the remainder will be 1. Want to look for another example. Now, this is question 11. Want to begin with part A. And let me just see try to understand what we have written here. 66 more than 13. Because 66 here is the remainder. 60 is the remainder. But now, this remainder is bigger than 13. So you have to reduce it to a number less than 13. So we again divide 13 into this. This 66. We divide 13 into that and see what the remainder is. So in fact, what we've been given here is this more than 13. So again, just divide 13 into this and see what the remainder is. So 13 into 66 will get 4. 66 divided by 13, we got there 51 times. 51 times. So what is the remainder there? 6 times 1 by 13, the remainder is 3. The remainder is 3. Yes, the remainder is 3. So what we have is this. So 666 is the same as 3. What was the question? The question was find a number m when multiplied by 666 would give us 1. Not the 13. That is, find the inverse of 650. So it is the same as finding the inverse of 3. Because we found that 3 is the same as 650. So this question can be written as 3m is congruent to 1 mod 30. In other words, find a number which, when multiplied by 3 and then divided by 13, will give you a remainder of 1. Let me use the extended Euclid's algorithm original. Extended Euclid. I can think of that. Because this is, for example, if I have 9 times 0 will be 20. 27. Yeah, 9 will be. Because 9 times 3 will be 27. And 13 into 27, the remainder of the 1. But since I've already said I want to use the Euclidean algorithm, let me just proceed. But I've already seen that the answer will be 9. Let me see. 3 into 13 will be 4. And the remainder will be 1 into 3 will be 3. And the remainder will be. So now I reverse this expression. We get 1 is 13 minus 4 multiplied by 4. So what this then means is that if I have negative 4 and multiply by 3, the answer will be 1. So in other words, m is negative 4 mod 13. But what is this? Because the remainder must be positive. So what I told you earlier I just said I add this to that. I get 9. So if 13 were to go into negative 4, the remainder will be 9. So then the inverse of 666, the inverse of 66 mod 13 is just 9 mod 13. Because it will be the same as the inverse of 6, then it will be the same as the inverse of 3. That is just 9. Let me do the other question. B. You want the inverse, you want a number which when multiplied by 5 to give us 1 mod 23. That's what the question is saying. The question is saying find the inverse of this. So in other words, what number when multiplied by 5 will give us 1? 5 is already smaller than 23, so we don't need to reduce it. So let me just use the extended Euclid's algorithm very fast, because I don't want to waste time thinking of the number. Let me use the extended Euclid's. So 23, 5 will go there 4 times, and the remainder will be 3. And into 5, it will go there once, and the remainder will be 2. And into 3, it will go there once, and the remainder will be 1. And into 2, 1 will go there twice, and the remainder will be 0. So now I reverse from here to reversing. I have 1 which is same as 3 minus 1 by 2, which is the same as 3. Let me put a 1 minus 1 instead of 2. Instead of this 2, we write 5 minus 1 by 3. Then put a 1 here. So this is negative 1 multiplied by 5. I'm doing the bracket first. Then this will be positive 1, and the other positive 1, it will be positive 2 multiplied by 3. So I now have these 3, which I want to replace. The 3 is there. So negative 1 multiplied by 5 plus 2 multiplied by 3. But what is 3? 3 is 23 minus 4 multiplied by 5. And so what is this? I want to do the bracket first. It's 2 multiplied by 23. And this is negative 8. Negative 8. And there's a negative 1. So that is negative 9 multiplied by 5. So what do I have? I have 1 which is equals to 2 multiplied by 3 minus 9 multiplied by 5. What does this mean? That if I have negative 9 multiplied by 5, the answer will be 1. So in other words, negative 9 is the inverse of 5. But I want it to be positive. Let me just create the space. I want it to be positive. The remainder must always be positive. So I'm looking for value which will multiply by 5 to give me 1. And I've just obtained that value. As negative. And mod is equal. So what I have therefore is that x is negative 9 mod 23. And since I want it to be positive, I would add this negative 9 to 23, get 14. So 14 therefore is the inverse of 5. The inverse of 5 is 14. In other words, 14 times 5 would be 1. On division by 23, it would be 1 as the we now look at part C, and part C is introducing a slightly newer concept because we want to find the inverse of 7 raised to 13, 7 raised to 13 mod 13. And as I said, you have so many ways, and even others are easier ways of finding this inverse. But from the very beginning, I said that I'll be using the extended Euclid's algorithm, and that is a method I want just to proceed with. But I'll introduce something slightly different in this one. But as I said, this number is too big. 7 raised to 13 is too big. It's bigger than mod 13. And you know it's the remainder, so we must reduce it to a number less than 13. And so once you reduce it to a number less than 13, we now get the inverse of that number. And that inverse shall be the same as the inverse of this. So I'll use squares. I'll use squares to reduce 7 raised to 13 mod 13. I'll use squares. So I know that 7 raised to 1 will just be 7. What about 7 raised to 2? What I've written here is the remainder mod 13. What I've written there is the remainder mod 13. What about 7 raised to 2? It will be 49. 49, 13 goes there. How many times? And what is the remainder? So I'm interested with the remainder. The remainder will be 10 mod 13. Because you just have 49. So 49, how many times does 13 go there? And this is my calculator. 49 divided by 13, it goes there 3 times. So 49 minus 33 times 13, that gives me 10. Now what about 7 raised to 3? 7 raised to 3 is the same as 7 raised to 2 plus 1, which is the same as 7 raised to 2 times 7 raised to 1. But 7 raised to 2 is 10, and 7 raised to 1 is 7. which is 70 mod 13. So if 13 were to go into 70, what would be the remainder? The remainder would be 5. That's what I'm interested in. What about 7 raised to 4? 7 raised to 4 will be same as 7 raised to 3 plus 1, which is 7 raised to 3 times 7 raised to 1. I'm just using laws of indices. Just using laws of indices. This is equals. This is equals. But 7 raised to 3 is 5. And 7 raised to 1 is 7. That is 35. So if 13 were to go into 35, what would be the remainder? The remainder would be 9. Now I want to do this until I find 7 raised to 13. So I'm at 7 raised to 9, 7 raised to 4. I can quicken my steps by now raising it to a bigger number, like 7 raised to 4. If I square it, I'll get 7 raised to 8. 7 raised to 8. But I've just squared it. That means 9 times 9, which is 81. But what is the remainder when 13 is going to 81? Because that is 7 raised to 4. 7 raised to 4 is 1. So 9 is square. So 9 times, which is 81. So it is close there. The remainder will be 3. What about 7 raised to 9? I have 7 raised to 8. So 7 raised to 9 will be 7 raised to 8. Then 7 raised to 1, which is 3 times 7, which is 21. If 13 were to go there, the remainder would be 8. The remainder would be 8. Now, so I want 7 raised to 13 actually. But this, I can now work it from here. It's just the same as 7 raised to 9 plus 4. 13 is 9 plus 4, which is 7 raised to 9. 7 raised to 9 times 7 raised to 4. But 7 raised to 9 is 8. And 7 raised to 4 is 9, which is 72. If 13 were to go into 72, what would be the remainder? The remainder would be 7. The remainder would be 7. Let me just see. That is 72. 72. 13 goes there 5 times. 5 times. So 72 minus 5 times 13, left with 7. So you can see I've used squares to arrive at 7 raised to 13. So 7 raised to 13 is the same as 7. So what I mean here is that if 13 were to go into this number, if 13 were to go into 7 raised to 13, the remainder would be 7. So finding the inverse of 7 raised to 13 is the same as finding the inverse of 7. Those inverses will be the same mod 13. Now, look at what I've done. I've raised 7 to 1 to 2 to 3 to 4 to 8 to 9 all the way up to 13. You don't need to always come up with that. Do all this. Don't need to do all this. You can just reach somewhere and then calculate, find out the shortcut of. For example, if I move from here, suppose I just want to come up to here, and then from here, how do I arrive to that? Let me see how I would have done. Suppose I just arrived at 7 raised to 3. Then I now work with 7 raised to 3. Although it's always easier to try and move as close as possible, because it becomes very easy for you to find what you want. But now, suppose I just came up to here. Let me pick my pen first of all. Suppose I just came up to 7 raised to 13. No, 7 raised to 3, and I want 7 raised to 13. Then I must know that 7 raised to 13 is the same as 7 raised to 3 raised to 4. then plus 1. What I mean here is that it's the same as 10 raised to 12 plus 1. 10 plus 1 is 13. But now this 12 is 7 raised to 3. 7 raised to 3, which I have. 7 raised to 3, what was it? We had said it is 70 mod 13, we had said that this would be 5. We had said that this would be 5 mod 13. So it will be 5, 7 raised to 3 is 5, then raised to 4. Then times 7 raised to 1, which is 7. Because this is from here. From here, what I'm saying is what I have is 7 raised to 3 raised to 4, then times 7 raised to 1. Because of the indices, these are just indices. And the 7 raised to 3 is what I've written as 5. Then raised to 4 now. I'm only by 7. So what do you get? 7 raised to 4, my calendar says 7 raised to 4 is 625. And then multiply by 7 to get what? We get 4375. 4375, and do it mod 13. Do it mod 13, divided by 13, and find the remainder. So 13 goes there 336 times. 336 times. So let's find the remainder. 4375. 4375 was going there 336 times. What will be the remainder? The remainder will still be 7. The remainder will be 7. That's why I say you don't need to come very close. If you can even do a few steps and then strategize on how to get 13, that will be okay. So we've now found that 7 raised to 13 is the same as 7 mod 13. So we want the inverse. And that is what we want to do. And to find the inverse, we've already done it before using the other methods, Euclid's algorithm. And to show you the same thing we are doing. That's why I said I want to stick on one method in these examples. Now, so the inverse of 7 raised to 13 mod 13 is the same as the inverse of 7 mod 13. So we want to find a number x. When multiplied by 7, it gives us 1. It will give us 1 mod 13. That will be the inverse. So we just use the Euclid algorithm. In fact, without using the algorithm, I can see that 2 is the answer, because 2 times 7 will give me 1. Because 2 times 7 is 14. And 13 into 14, the answer will be 1. So the required inverse is 2 mod 13. Is 2 mod 13. That's the required inverse. I want to do the other question, and I hope it now be clear to you what we're supposed to be doing. D. We want the inverse of 8 raised to 15 mod 17. Again, I use squares to reduce 8 raised to 15 mod 17. So what is 8 raised to 1? 8 raised to 2 is 64. I'm doing it mod 17. So 17 into 64. And I want to plot what I can get. 17 into 64. I want to use my calculator here. What will be the remainder? The remainder will be 13. What about 8 raised to 2? 8 raised to 2, no, 8 raised to 3. 8 raised to 3, which is 8 raised to 2 plus 1, which is in fact 8 raised to 2 times 8 raised to 1. But 8 raised to 2 is 13, and this other one is 1, 8. So the answer that you get divided by 17, because you're doing it mod 17 and write the remainder will be 2. And now from here, it's now easier. It's now easier now to find 8 raised to 15. Because I don't need to proceed looking for the rest. Because I don't know that if this is very small, I can raise it to, because it will be the same as 8 raised to 3. And if I raise it to 4, if I raise this to 4, or 5, just 5, then I'll be having 8 raised to 15. But 8 raised to 3 is 2. And this one is 5. Mod 17. What is 2 raised to 5? Using my calculator, 2 raised to 5 is that 2 divided by 17, because there are 17, so 1 time. So that 2 minus 1 times 17, the answer is 15. So you can see, I didn't need to go to 8 raised to 2, 8 raised to 3, no, 8 raised to 3, 8 raised to 4, 8 raised to 5, all the way. I just switched here and I saw that I did a very small number. And I can use this smaller number now I can raise it to any power and do it with a calculator. Now, so then what that means is that 8 raised to 15 mod 17 is the same as 15 mod 17. So in other words, the inverse of this is the same as the inverse of this mod 17. Let me just find the inverse of 15 mod 17 and see what it is. I've used Euclid's algorithm. So 17, using Euclid's algorithm, using Euclid's algorithm, 17, 15 would go there once, and the remainder would be 2. What about 15? 2 go there 7 times, and the remainder would be 1. What about 2? 1 will go there twice, and the remainder would be 0. So I now reverse this. So reversing the first one here, making 1 the subject. 1 is 15 minus 7, 2. I can put a 1 here. And this is 1, 15 minus 7. Instead of 2, I write its equivalent, which is 17 minus 1, 15. And so what do I get? I want to work out the bracket first. And then it's working out the brackets here. I have negative 7 times negative 1, which is positive 7. This positive 7 plus this 1, it gives me 8. Positive. Times 15. Actually, I wanted the inverse of 15, and I have it as 8. I have it as 8. So that again is the inverse of what was asked. So the inverse of this is therefore its inverse is inverse just 8 or 17. So that is how you do this kind of. If it was 8 raised to a number raised to another one. Of course, there are other easier ways of like rule of 5 theorem and Fermat's little theorem. In this video, I said I would just stick to one method, which is the extended Euclid's algorithm. Now, very related to been doing is this question 12, which I find the remainder when 15 multiplied by 23 is divided by 13. And I've said that this question one can rephrase it and just say find 15 times 13, 15 times 23 mod 23, mod 13. Now, so how do we do this? We find the remainder. First of all, do the 15 mod 13, and then you do 23 mod 13, and then combine the two results, because this is like it out. Now, so this is the remainder, and we can reduce it. If it's larger than 13, you can reduce it just to 2 mod 13. That is, if 13 goes there, the remainder will be 2. And again, this is 23 larger than 13, you can reduce it to mean what? Is it 10 mod 13? That is, if 13 were to go in 23, the remainder will be 10. Now, so therefore, what is 15? Therefore, what is 15 times 23 mod 13? This will be the same as 2 times 10 mod 13, but of course this is 20 mod 13. 20 is larger than 13, so you reduce it to 7 mod 13. So that is the remainder. If 13 were to go into 20, the remainder would be 7. And that's how you do this question. That's how you do it. You don't need to multiply the whole of it here. And then, in fact, you can do that, but in some cases you find that the number will be larger than what your calculator can accommodate. The number will be larger. For this example, I think this is a very small number. You can still multiply 15 times 23, and then divide the result by 13, and then note the remainder, and the remainder will just be 7. Let's look at the other question. Question 13 says find the remainder if this number was to be divided by 12. If it was to be divided by 12, I've gone to another different question. I wanted 13. So I just did the same way I've done the other one. This question is the same as 14 times 38. Find this mod 12. So first of all, I would do 14 mod 12 and find that the remainder is 2 mod 12. 38 is also larger, than 12. So if 38, let me see what would be the remainder again. The remainder again would be 2 mod 13, because 12 will go there 3 times, and because of that 6, subtract to get the remainder to be 2. And so, what do you want? It is 14 times 38 will just be 2 times 2, which is 4 mod 12. So that is the remainder. So if I was to multiply this 2 and divide it by 12, the remainder would be 4. That's how we do it. Let me look at another one slightly different that you can see how to find the remainder. Just want to see how to find the remainder. Find this mod 7. Is the same as find the remainder when 3 raised to 31 is divided by 7. So again, we just do the same we've been doing here. It is we use squares. Use squares. We just want to find the remainder. 3 raised to 1, that will just be 3 raised to 2. That would be 9. That would be 9 mod that would be 2. And then you can also do the raised to 4, there's no problem. The raised to 4 will just be the raised to 2 square. which is 4. Then you can also do, even from here, you can say, what about 3 raised to 16? This will just be 3 raised to 4 raised to 4. Just trying to see how I can arrive at this easily. And this will just give you 4 raised to 4. Using my calculator, that will give me 4. That gives me 4. I'm doing it mode 7. Doing it mode 7 because we are dividing by 7. So 4 raised to 4, what is it? 4 raised to 4 by using a calculator, that would be 256. 256 divided by 7. Divided by 7, you get that 6. So 256 minus that 6 times 7. The remainder is 4. That's why I've written it 4. Then from there, what do I want? I want this 1 to 3 raised to 31. 3 raised to 31. In fact, this one twice to the square root of 32. It's slightly higher than that. But I can work, I can say it's 3 raised to 16. Then I can even talk of 15 here. 15 here. And the 15, that gives me 31 action. So I want to see, just playing with these things. 3 raised to 16, I have it. 3 raised to 16, I have it. What I'm lacking is 3 raised to 15. 3 raised to 15, I'm lacking that. But I have 3 raised to 4. I have 3 raised to 4. And I know that 3 raised to 4, if I cube it, I'll be having 3 raised to 12. So 15, I already have 12. So what I'm lacking is 3 raised to 3. And it can be 3 raised to 2 and 3 raised to 1. Let me just see what I've written. What I've written here is 3 raised to 16 plus, what is this? This is 12. What is this? This is 2. What is this? That is 1. So what do I have? This is 48. 28. This is 28. 28, 29, that's 1. Yeah, I have what I want. So I'm just playing with what the few I have. So 3 raised to 16, I know it's 4. Then time using this. 3 raised to 16 is 4 times 3 raised to 4 is 4. But that 4 I raise it to 3. I raise because this is 4. This is 4. Then raised to 3. 3 raised to 2, I have it as 2. Then 3 raised to 1, I have it as 3. Let me see what I have. Give me my calculator now. If I use my calculator, 4 times 4 raised to 3, then times that 6. I get 1536. 1536. Remember, it's mod 7. Now divided by 7. If we go there 219 times. 219 times. Let's find the remainder. 219 times, let's find the remainder. 219 times 7 from that is 3. So I have 3. In other words, the remainder, when 3 raised to 31 mod 7, the remainder of this, when 3 raised to 31 is divided by 7, the remainder will be 3. Now I want us to look at this other one and see, and again, see how to do it using squares. was the question, although they have not said find the remainder, but that is what the question is. We are always fighting the remainder. This is just what is here is just the remainder. What is coming before the mod there is the remainder, but you can see it's a very big value. So just reduce it. Reduce it to, but first of all, we can reduce even 128 first of all. Reduce 128 first. Reduce 128 first because it's also very big before we even come to the power. So 17 into 128, what is the remainder? Using my calculator, I get 9. So that means when I talk of 128 raised to 120 mod 17, and somebody else talks of 9 raised to 129 mod 17, then we are talking about the same thing. We are talking of the same thing. But now I want to reduce it. Now reduce, because it's also very huge. This is also very huge. Reduce 9 raised to 129 mod. Reduce it using squares. You just use squares. So 9 raised to 1 is just 9. And just do it very fast. What about 9 raised to 2? I use my calculator. The remainder will be 13. Just writing the remainder. So I say that repeatedly so that somebody gets lost. So you can get your way. 9 raised to 4 will be 16. I'm writing the remainder mod 17. Then 9 raised to 5 to 8. What about 9 raised to 10 to 13? And you know that how did I get this? This 9 raised to 13, 9 raised to 10, just 9 raised to 5 square. So just square 8. Yeah, it will take 9 then raised to 10. In some cases, you find that a value that your calculator cannot accommodate. That's why I'm using the one just to the previous one. 9 raised to 10 is 9 raised to 5 square, which is 8 square. And mod 17, that would give us that. Even this 9 raised to 4, I just put 9 square, then square. And then what about 9 raised to 20? It just be 13 square, which is the what? 16. Then what do I want? I want to think of the easier way of arriving at that. Let me do one more. 9 raised to 40. It will be 9 raised to 20 square. In fact, this is 16 square. Mod 17, that gives me 1. That gives me 1. That one is the remainder. Now, once I get 1, it becomes very easy for me because now I can relate 40. Because what I want is 9 raised to 129, but I have 9 raised to 40. So now I see the relationship between 40 and 121, 129. I want to see the relationship using the Euclid's algorithm. Then from there I get the answer that I want. So let me go straight to the relationship using the Euclid's algorithm. Now, what is 129? 40 goes there how many times? 40 goes there 3 times. I think it's 3 times because of 120. And the 9 will be the remainder. So in other words, if I have 9 raised to 129, this is the same as 9 raised to 40 times 3 plus 9. But this is the same as 9 raised to 40, then raised to 3, and multiply by this. It's 9 raised to. But 9 raised to 40 is not. Is 1. So this first part is just 1 raised to 3. Then 9 raised to 9. But 1 raised to 3 is just 1. What about 9 raised to 9? So this part, the first part is just 1. So I ignore it. Then 9 raised to 9, I can manipulate this to see how it goes. Because I know 9 raised to 4 squared plus 1 is equal to 9 raised to 4 squared times 9 raised to 1 using the laws of indices. But 9 raised to 4 is 15. What about 9 raised to 1? It's just 9. We are doing it mod 17, so let's just multiply 16 square. That one our calculator can accommodate. It's 256 times 9. That is 2304. 2304 mod 17. So in other words, if 17 were to go there, what would be the remainder? 17 goes there 135 times. 135 times. So 2304 minus 135 times 17 gives us a remainder of 9. There's a remainder of 9. That is the remainder. That is what the question wanted us to do. The question wanted us to find the remainder. We do it the same way we did an earlier question. First of all, we find 3 raised to 31 mod 7. And then we find 2 raised to 35 mod 7. Then we add the 2 results. So let me begin with the first one. Using squares. What is 3 raised to 1? What about 3 raised to 2? We are doing mod 7. That would be 2. I want 3 raised to what? What about 3 raised to 3? 3 raised to 3 would be 6. Would be 6 mod 7. 6 mod 7 is not 1. Mod 7. That means if 7 were to go into 6, we get negative 1. So I'm using a smaller number so that I can work very fast. But what I want is 3 raised to 31. I want 3 raised to 31. I want to see the relationship between this power and this. So 31 by Euclid's, what do you get? 3 goes there 10 times. 3 goes there 10 times. And the remainder is 1. So that means when I take 3 raised to 31, this is the same as 3 raised to 10 cubed. I don't know this term. What I have is 3 raised to 3. So it's 3 raised to 3, then raised to 10, plus 1 here. Let's multiply by 3 raised to 1. But 3 raised to 3 is negative 1. We have negative 1 raised to 10. Then times 3 raised to 1, which is 3. And a negative number raised to an even number. So this will be 1 times 3. So the remainder, if 7 were to go into 3 raised to 1, would be 3. That's the remainder of the 10. So the only question I know people asking at this point, this was 2. 3 raised to 3. is the same as 3 raised to 2 plus 1, which is 6. So you would as well have, you would still have written this the same thing. But then every time you make it smaller, it becomes easier for you. Because this you can make it smaller. If 7 were to go here, the remainder would be negative 1. If 7 were to go there, the remainder would be negative 1. Also to go there one time. 7 into 6. Go there. 1 times 1. So 1 times 7 will be the only subtract. The remainder will be negative. So that is what I wrote here. But what I'm saying is not bad for you to have used 6. You still have used 6. And you can as well proceed and proceed and proceed and move very close to that one as you can do for the other questions. Now, so we found that this is 3. Let's now do this other one, then we shall add. Oh, this, let me write here. 3. I want to do for this other one, and then we add the 2 results. Now, I want to do now 2 raised to 35, but I know what 2 raised to 1. I know what 2 raised to 1 is. It's mod 7, and then 2 raised to 2, I know it's that, mod 7. What about 2 raised to 3? It would be 8, mod 7, that is 1. So I've already found something which is smaller, so I can work with that. I wanted a 2 raised to 5, but I know what I have, that 2 raised to 3 is 1. I need to write this that 5 in terms of 3. What is that 5 in terms of 3? I know that 11 times 3 would be that 3, and the remainder would be 2. Yes. So that means 2 raised to that 5 is the same as 2 raised to 11 times 3 plus 2, which is the same as 2 raised to 3 raised to 11 times 2 raised to. But 2 raised to 3 is what? Is 1. 1 raised to 11 times 2 raised to 2. 2 raised to 2 was 4. And so the answer is, so the remainder there is 2 raised to what? Yeah, 2 raised to 2 is 4. So this is 4. So then this will be 0 what? 3 plus 4 more 7. This will be 0. So what that means is that if 7 were to go into this number, then the remainder is 0. But you will still have, you may want to go through these steps and see whether they're correct. You may want to go through the steps, but that is how you do it. That marks the end of part 1 of our revision questions in modern algebra. So next time we begin with question 17, which will be part of our part 2 of our revision questions. Thank you for watching. Subscribe to my channel so that whenever I upload a video, you can find the link automatically.